I introduce the next speaker of the session, Dr. Ashish Kumar Sen. He's a professor in Department of Mechanical Engineering at IIT Chennai. He received his BTech from NIT Roorkela, ME from IIC Bangalore, and PhD from USC Columbia. He has published nearly 80 research papers so far in various prestigious international journals and filed 6 patents. His area of research includes microfluidics and lab-on-chip based interfacial phenomena and healthcare diagnostics. I request Ashish Kumar Sen.
So good morning. I am Ashish Kumar Sen. I'm a faculty in Department of Mechanical Engineering at IIT-Madras. So morning we had 2 fantastic talks focusing on biological aspects of cancer cells, etc. So my talk will be on mechanophenotyping of cells using microfluidics. So this will give you more some kind of an engineering aspect of what is being talked about. So this is an overview of my presentation. First, I would briefly introduce mechanophenotyping, and then talk about some of the conventional techniques that have been used for mechanophenotyping of cells. And then we'll discuss some of the microfluidics techniques, which are actually high throughput as compared to conventional techniques, bothly from literature as well as some work that we have done in our group. And then I will end with some future perspectives. So this shows some beautiful picture of these coquina cells. It shows that depending on the species, you can have different coloration and patterns on the cells. So with regards to the mechanophenotyping of cells, first of all, what is mechanophenotyping? So it is nothing but differentiation of cells based on mechanical properties, and which actually originates from the genetic code as well as the effect of environment. So as you can see here, you can have circulating tumor cells which are quite different as compared to the normal cells, which are the PBMCs. Similarly, the fetal cells and the infected red blood cells would be quite different as compared to the red blood cells. And same is the case for sickle cell. So if you look at circulating tumor cells and compare with the lymphocytes, typically circulating tumor cells are much larger in size and they are more deformable. That means the stiffness is quite small as compared to the normal cells. So this shows, various kinds of cancer cells, starting from breast cancer to pancreatic cancer, and you can see the Young's modulus, which actually represents the deformability or the stiffness of cells. The cancer cell line consistently have much smaller stiffness or Young's modulus as compared to the normal cells. And you can also compare different kinds of cancer cell here. So here you see that this shows a relative Young's modulus, which is the ratio of the Young's modulus of a particular cancer cell to the normal counterpart. And you can see that, for example, per bladder cancer cell, the ratio is quite small. That means the bladder cancer cells are much more deformable as compared to the normal cancer cell, as compared to, for example, the esophageal cells, where the cancer cells and the normal cells stiffness is quite comparable. So you can look at what happens in case of sickle cell anemia. So typically, if you look at a structure of an RBC, if you take a cross-section, it looks like a dumbbell. And when you have sickle cell, the structure and morphology of the cell changes. It looks like a crescent shape. And the stiffness of these cells also significantly increase. And they also develop surface proteins which tend to, for which the cells tend to stick to each other. Also, they stick to the channel walls. So you have this blockage in the blood passes. This work shows how upon malaria infection, how the stiffness of RBCs change. So you can see for healthy RBCs versus that for the malaria-infected RBCs at different stages, starting from the ring stage to the scaden stage. So this uses a technique called optical tweezing. So this is the cell, RBC, and these two are beads. And by applying a light beam, you can actually move these beads far apart. So these are actually functionalized on the surface. They're actually bound to the surface. And when you try to stretch it, for the same amount of load, you can observe how these different cells would stretch. So you can see that a healthy RBC is giving a much higher elongation as compared to the final stage of infected RBC, which doesn't stretch at all. So this actually summarizes, the healthy RBC versus the ring stage and tropozoite and scasent RBCs, how the elastic modulus is increasing significantly. So the mechanical properties of the cells mainly come from, among other components, these microfilaments and the intermediate filaments, also the microtubules. So if you want to understand the mechanical properties of cells, you have to understand solid mechanics. So what happens if you have an object and you subject this to a force, depending on the direction of the force with respect to the plane of the object, you can have either normal stress or you can have tangential stress. And for an elastic material, the stress and strain, they are proportional to each other, and the constant of proportionality is known as elastic modulus. Similarly, if the stress is applied in the tangential direction, the stress leads to shear strain, and the shear stress and the shear strain are related using shear modulus. Okay? And if you talk about a soft material and you plot the stress versus strain, for a lower range of strain, stress and strain are proportional to each other. But when you go to the higher end of strain, the stress it increases very rapidly as you increase strain. So this is the case for soft materials like cells. Now, if you want to understand, what kind of tools that you want to pick for measuring mechanical property, you have to understand the lens scales. And so here, this shows starting from organ all the way to intercellular components. And the cells are typically of the order of size of tens of microns. Okay? And you also have to understand the time scales. And you see that depending on the cellular processes, it can vary from several days to about nanoseconds. For example, the protein dynamics happens very fast, of the order of nanoseconds, whereas the diffusion and polymerization and transport across cells typically happens of the order of a fraction of a millisecond or so. And talking about the mechanical strength of various cell objects, so you talk about eukaryotic cells, the elastic modulus is typically 10 to 100 Pascal. Okay? So when you want to study the mechanical property of cells, there are different loading conditions you can use. This shows when you subject the object to a fixed stress, fixed strain, so you just apply some strain and look at the stress behavior. So the stress actually relaxes over time. So this is one condition. The other condition is creep. So in creep, you subject the structure to a fixed stress and then look at how it is getting stressed, the strain behavior. And so this is called the rheological characterization. You can also characterize the viscoelasticity. So to be able to characterize viscoelasticity, typically you subject the structure to an oscillating strain. So when you do that, so this is gamma is the shear strain, and that goes as gamma naught sine omega t. Omega is the frequency of oscillation. And when you subject that structure to this, this is the response, okay, the stress response. So the stress actually lags strain with a phase angle phi, okay? And you can actually express stress in terms of two characteristic quantities. So these are called storage modulus and loss modulus, G prime and G double prime. And from that, you can actually calculate the dynamic modulus. Okay. So in elastic materials, the loss modulus is 0. Okay. So the storage modulus exists. So the total dynamic modulus is nothing but the storage modulus. But in viscoelastic materials, your stress would lag strain by phi equal to pi by 2. Okay. So there will be a 90-degree phase lag for stress against strain. And your G prime, the storage modulus is 0 for a viscoelastic liquid, and only the loss modulus exists. And this mu is viscosity, and omega is the frequency. So a cell is actually somewhere in between. Okay? So you can have viscous component, you can have elastic component also. Cell is viscoelastic, so you have to take care of both G prime as well as G double prime. Now, this slide shows you, depending on the technique that you use, what is the typical force that you apply. So if you use AFM, a typical force is in the range of piconewton to micronewton, whereas if you use micropipette aspiration, the typical force will be from piconewton to nanonewton. And the microbead rheometry, we will look at each of these techniques. The force is of the order of piconewton. And for optical tweezer, where you use light beam to stretch a cell, like as I was showing for a malaria-infected cells, the force is from femtonewton to piconewton. And for fluid-based deformation, the force is of the order of piconewton. So this slide shows the first conventional technique, which is atomic force microscopy. So typically in atomic force microscopy, you have the cell which is immobilized to a surface, and then you have a cantilever sort of structure. So typically for cells, you use a bead tip cantilever. And the way you do is you bring the cantilever tip and first deform the cell. So you make sure that the tip is in contact with the cell, and then slowly you raise it. When you raise it, when there is a very, very small gap, or that of 10 nanometer gap, you would observe that the tip will suddenly snap into the cell, and that is because of the Van der Waals attraction. So there will be a sudden dip that you observe in the deflection versus force plot. And that is where you know that the cell is in contact. And then you start applying force. So, and then as you apply force, the indentation depth and the force relation you observe. And there are various models are available. For example, you have Hertzian model, where by looking at the deformation characteristics, you can also predict what is the Young's modulus. The force deformation characteristic can give you the Young's modulus of that particular cell. So that is about atomic force microscopy. And then you have optical tweezing. So in optical tweezing, as I was showing for the infected RBC case, you have these beads typically attached to the cells, and then you shine light beam. And when you shine light beam, as compared to the environment, the cells have different refractive index. So as per optics, when you have a difference in refractive index, that leads to some kind of force. And when you drag this light beam, the bead attached to the cell also moves because of this optical scattering force. And when the bead moves, the cell gets stretched. And the stretching of the cell is quantified against the Young's modulus of the cells. Talking about the particle tracking microrheology, here there is no external force. Here particles are put inside the cells, and the particle actually moves because of the interaction between the particle and the elastic structure of the cell. So you just need to track how a particular particle moves with time. So this MSD is mean square distance. So by tracking how the particle moves, you will be able to know what is the Young's modulus of the cell. If it is a softer cell, the particle move much larger MSD as compared to a stiffer cell. Now, in traction force microscopy, here, the particles that you want to track are actually part of the substrate. And you put the cell. The cell would actually, so this works fine for adherent cells. The cell would like to move on the surface. When it does, it actually drags these particles along. And by tracking the position of these particles, you can get information about the stiffness of the cells. We'll come back to this. So here, this is another technique called the magnetic bead technique. So here you have the cells coated with a bead, and you subject this to a magnetic field. And this magnetic field, by applying a varying magnetic field, you can subject the cells to alternating stress, because you can switch on and off, and so that the bead moves back and forth. And when you do that, you track the bead displacement and make sure that this bead is a ferromagnetic bead, because it should respond to the magnetic field. So by varying magnetic field, when you track the bead displacement will be correlated with the property, the mechanical property of the cell, the stiffness of the cell. So this information can be translated to obtain mainly the storage modulus, and loss modulus we can give you the total modulus. And this is another technique called parallel plate rheometer. So here you have the cell resting on the surface, and the top surface you bring in contact, and you apply an oscillating load on the cell. When you do that, the cell deformation also you're simultaneously tracking using optic, and the deformation of the cell and the load are correlated. So here, by applying a different frequency, you can actually measure the elastic stretching and loss, elastic and loss modulus, and which can help you to get the total Young's modulus of the cell. Talking about the micropipette aspiration. So typically here, you have a pipette structure, which is micron in orifice size, and you subject this system to a negative pressure. So when you apply a negative pressure, the cell tries to get in, and depending on the pressure and the stiffness of the cell, this length of the cell that gets into the pipette is characterized. And so you basically have here on your y-axis, you have the applied pressure, that is the atmospheric pressure minus the negative pressure, and then the x-axis is the aspiration length, which is normalized with respect to the cell size, for example. So as you increase the pressure, you have higher and higher length of the cell getting into the micropipette. And for a cell, so if you do some mechanics, for a cell, you define something called cortical tension. Like if you have a liquid drop, small enough, and you leave it in air, it tends to be spherical, and that is because of surface tension. Similarly, there is a property of a cell to maintain its sphericity, and that is known as cortical tension. And that cortical tension would affect how much of the cell would enter into the micropipette. And once you know the cortical tension, you can calculate, there are correlations available to calculate the Young's modulus. So this is called the rheology, where you have two plates, and you dispense the cells on the bottom surface, and you bring the top plate, and you subject this to oscillating shear. So, but it is rotating, okay, not translation. So this rotation of the stage and you can observe how the cells are getting deformed, okay. And by studying mechanics, by using mechanics, you can actually, this deformation can be translated to, again, shear modulus. So this slide shows the aging of the cells. So as you leave cells for a longer time, the stiffness of the cells would increase with aging. And people have also tried to use drugs to control stiffness of cells. So most of these drugs are tried against the cells, which shows that the elastic modulus, most cases have decreased, but then there are certain cases where drug treatment have increased the elastic modulus of cells. Now, all these conventional techniques, if you see, and you talk about the throughput, maximum you can see this optical technique can give you something like 2,000 cells per hour, right? So that is still about 30, 40 cells per minute, which is quite small if you want to look at a large amount of cells and you want to characterize them. So that is where the microfluidic techniques becomes very useful. So here I would talk about these methods. So one is flow-induced, second one is optical stretching, and then compression, aspiration, and constriction deformation. So in flow-induced method, so what you do is you flow the cell through a narrow constriction. So here RBCs have been flown in through this narrow constriction. This constriction size is about 10 micron or less. So when you flow these RBCs, depending on the shear stress that you apply, they can exhibit different kind of motion. So this is with increasing shear, RBCs have shown from stretching. So stretching is just the cell dimension in plane increases. It has also shown tumbling. If the shear stress is still higher, the cells can tumble. Okay, so if you look, it can do like that. Okay, so that is tumbling. It can also recoil. Okay, so all these cell dynamics can be controlled by controlling the shear in narrow constriction. People have also applied, subjected cells to just shear stress at a junction. So these cells are flown in, and you have some liquid also coming from the opposite direction. So here you can see the spherical MCF7 cells as it comes and tries to bend 90 degrees. So you have some additional flow coming. So that leads to deformation of the cell because of excessive shear. And they have studied how, depending on the diameter of the cell, the deformability. So this is basically an index, which goes as if you have an elliptical shape. A is the major axis and B is the minor axis. The deformability index is nothing but A minus B over A plus B. And that means if a cell is very stiff, it doesn't deform at all, the deformability index is going to be 0. And if it is 1, then it is highly deformable. And in microfluidics, people have tried optical stretching. So this, as I was saying, when optical beam crosses the cell, because the cells have different refractive index as compared to the medium, it leads to scattering force. And this scattering force, if it is asymmetric, the cells can move from its original streamline to another streamline. However, if the optical scattering force is symmetric and it is large enough to overcome the drag force that tries to take the cells away, you can actually trap cells. You can trap cells, you can also trap and stretch cells. So this shows how the cells have been stretched, so its size has increased because of optical tracking. And then this optical deformability that you define the deformability index, how I told in the previous slide. So this optical deformability is a representation of the stiffness of the cells. Here, people have used compression techniques. So here you have a channel configuration like cross. In one channel, you have the cells flowing. In other channel, you have a controlling liquid flowing. And both these channels are separated by a soft membrane. And when you increase the flow rate of the controlling fluid, the membrane deforms downward because of the excessive pressure. And that pressure can actually tries to stretch cells. So as you can see here, so this is 3T3 cells. At 0 second, this membrane is stretched, right? So this diameter has increased. Now if you remove the pressure, excessive pressure, you can actually observe how the cell is relaxing back to its initial state. And this is shown here for two different cells, 3T3 and HL60. So so this is called compression ratio, and this is recovery time, how the cell is recovering from its original compressed state to its initial state. So this compression ratio is the time instant diameter to the initial diameter. So if this is, the initial diameter divided by the time instant diameter, if this is small, that means the cell has been compressed to a great extent. So the recovery time will be much higher. And if the cell is not stressed to that extent, the recovery time will be less. So by measuring recovery time, you can actually get an indication of the stiffness and deformability of the cells. If a cell is very stiff, the recovery time will be small. And if it is deformable, the recovery time is going to be longer. This is aspiration technique. So you have a microfluidic channel, but then you have a channel cross-section here which actually mimics like a micropipette. So when you flow cells, so here if you don't have any constriction, for example, this constriction size is equal or greater than the cell size, cell will nicely flow, and then pressure linearly decreases as you'd expect for flow in a microchannel. But if you have a constriction which is much smaller in dimension, what happens is when the cell gets there, so you have this hydrodynamic pressure from here to here, which linearly decreases, but slowly. But then across this junction, where the cell is blocked, you have a very sharp reduction in pressure. And then further, you have this slow decrease in pressure, almost parallel to here. But this jump is because the cell is getting stuck at the junction. So this is, and when you have this constricted shape, the cell actually gets deformed. So it has to elongate to pass, right? And that deformation index is represented here. And TC is the time that it takes to pass this constriction, okay? So for various cells, they have tried, and they have shown that they all fall within a band. Now, it also depends on how much pressure that you apply. If you apply large pressure, the deformation is going to be very large. And if you apply small pressure, there may be some leakage across the cells. That means the cell is not entirely blocked. So you have small deformation index. So people have tried to find out the cortical tension. As I was saying, using mechanics, you can find the cortical tension of the cell. And this cortical tension, people have tried to find for various different kinds of cells. And this is, again, a similar technique, constriction-based technique, where here, an RBC followed by a WBC is flowing. And you can see that as a cell approaches the constriction, the pressure starts to fall. And the pressure keeps on decreasing until the cell is about to exit the constriction. So that is where the minimum pressure is, because it is completely blocked there. And then once it comes out, the pressure comes back. And people have tried to do that for various types of cells. So you have these single RBCs, and people have tried to treat RBCs with something like diamide and glutaraldehyde, etc., and which basically tend to stiffen red blood cells, and seen these pressure time characteristics. So in our lab, we have done a couple of techniques to characterize mechanical properties of cells. And one of the things that we have used is called hydrodynamic resistance. So when you have, let's say, flow of cells in a channel, you can think of pressure is equivalent to voltage, and the flow is equivalent to current. If there are no cells present, you have large current, you have large flow. When you have cells present, because of the hydrodynamic resistance, the flow actually reduces, the velocity reduces. And we want to know how this change in resistance is related to the size and stiffness of the cell. Now, size effect has been well addressed, so we were interested to know what is the effect of the stiffness of the cell on this change in the increase in hydrodynamic resistance. So you can actually flow these cells of different stiffness, and you can carefully monitor the pressure across the section of the channel. And the difference between when the cells are present versus cells are not present gives you this hydrodynamic resistance. So this delta RD is when you have a cell present in this section versus when cell is not present versus the initial resistance. So you can see that for these different kinds of cells, starting from this MDMB to HeLa, which is very stiff, your hydrodynamic resistance increases rapidly from a very small value to a very large value. We have also used AFM to characterize cells to support what we have observed here. And so this is what I was talking about. So you have already the probe in contact with the cell, and when you release it, suddenly, if the spacing is about 10 nanometer, you have a sudden snap because of the van der Waals. And then when you apply loading, it gets deformed. And from there, you can actually, when you know the deformation parameters and you know the radius of the cell, you can actually calculate Young's modulus. So that is how, from the force and indentation, the Young's modulus of various kinds of cells are calculated. And this actually agrees with what we have observed in terms of the hydrodynamic resistance. Now, we have used that for cell sorting. So this is a particular design. So this is a design that we have used to sort cells based on stiffness. You can see that this is where the cells are coming, and this is a sheath fluid. So this section, we call it as a sensing region. So what happens is, when you have a cell here, it can alter the flow distribution into this branch versus the straight branch. If you have a stiff cell, then it will reduce this flow significantly, whereas, so the more flow will go in this bypass channel, and less flow is going to come this branch. So in that case, the cell, if it is stiff, cells have a tendency to flow into a higher flow rate channel at a junction. So since this flow is reducing because it's a stiff cell, the stiff cell is going to continue straight. If it is a deformable cell, then this resistance is less, so you have less bypass flow, so you have more flow into this branch. So the deformable cell is going to come into this branch. So there is some fluid dynamic analysis involved. I'm not going to detail. So that means the sensing region can actually know whether the cell is stiff or deformable. Of course, you can have a critical value of Young's modulus, so where the cell neither goes into this or this branch. And by operating around that, you can sort cells that are of higher stiffness than this critical value and lower stiffness than that critical values. And we have used that to actually sort PBMC, these cancer cells from PBMCs. We have also used a microfluidic device for high throughput measurement of stiffness of various kinds of cells. So you have these cell samples coming. So the design is such that you have only one cell entering each one of these channels. And by measuring the elongation characteristics, you can predict the stiffness of the cells. So these are some how much time they take to pass through the narrow constriction, and how much they actually deform is characterized for different types of cells. And we have a mathematical model by observing how much the cell elongate and how much time does it take to pass through the constriction to predict the Young's modulus, and we have verified that with the measurements that we have gotten from AFM. Now, the last part of my talk, I'll take about another 5 minutes. So, if you look at the size distribution of cancer cells and compare with PBMC or white blood cells, there is a large overlap. So people have attempted in literature using size as a marker to separate white blood cells from cancer cells. But there have been a lot of debate because there is a good size overlap between the two. We have exploited another parameter called acoustic impedance. Acoustic impedance is nothing but the product of density and speed of sound in a medium. It's rho into C. So if you look at different cells and look at the overlap in acoustic impedance of the white blood cells with respect to different cancer cells, the overlap is actually very small. So what we have done is exploit this acoustic impedance property to separate cancer cells from the white blood cells. And we use a technique called acoustofluidics. So this is a technique that we have started in our lab last couple of years, and we are going forward with this as a promising technique because it can handle much higher throughput as compared to other microfluidic technique. So in acoustic fluidics, you have a channel cross-section here, and you have a regenerator. So you generate what is called a standing wave. So you have a regenerator which sends an incident wave, which gets reflected because the channel design allows that. And the superposition of incident and reflected waves gives you standing wave. So you have node here and you have antinode here. When you put some particles or cells into the channel, these cells are going to see some acoustic radiation force because of the difference in the acoustic property of the cells and the medium. And that force is given by this expression. And here A is the size of the cell, and phi is a parameter called contrast factor. So this is very important because this is very specific to cells. The contrast factor is a function of density of the particle and density of the medium, and compressibility of the particle and compressibility of the medium. So what we have seen is when you put a particle that have got positive contrast factor, those particles tend to go to the node. That has got negative contrast factor goes to the wall. For example, if you put milk, the fat in the milk has negative contrast factor, so you would see all the fats going to the walls. And if you put, let's say, blood sample, the blood cells have positive contrast factor, then tend to go to the node, the center of the channel. So in this way, you can actually separate particles. Since you have size dependency and it is Q, you can actually sort particles based on size. Since it is also dependent on phi, which is dependent on the acoustic impedance, you can also sort particles based on the acoustic property. So we have used this technique to separate cancer cells from PBMCs. So here what happens is you have low impedance medium containing the cells coming through the side inlets and high impedance sheath fluid at the middle. So what you do is, depending on the cancer cell, you control the acoustic impedance of the medium so that if the medium and the particle impedance match, the particles will not move. Okay, so these white blood cells will not move. So the white blood cells just simply follow the streamline that they are in. Whereas these cancer cells, since they have, in this case, higher impedance as compared to the cancer cell, the white blood cells, these positive contrast factor cancer cells will move to the node, and then you can collect at the center, whereas the PBMCs can be collected at the sides. On the other possibility is the CTC's impedance is low. In that case, what you do is you have the high impedance medium contains the cells, the mixture of PBMCs and cancer cells. So you again match the impedance so that these white blood cells don't move from their original streamlines. In that case, the cancer cells will have negative impedance, acoustic impedance, so they will migrate to the wall. So depending on the cancer cell that we are handling, we just control the property of the medium to arrest the movement of the white blood cells, and the cancer cells will move either to the wall or to the node depending on their contrast factor, whether it is positive or negative. So this is again a positive contrast factor coming to the middle, 0 is stay where they are, and negative is they move to the wall. And so we have actually used this iodexional solution to control the impedance of this suspending liquid. So impedance of that was controlled by controlling the percentage of impedance. So you can have all positive, that means positive contrast factor, negative, negative contrast factor, 0 is where the white blood cells will stay stagnant or they just follow the streamline. So we have used that, and I think these are some videos. Oops. So what you see here is just are following the streamline, they're not changing streamline. Whereas CTCs are individually tried out, and when you mix them, you can say that the PBMC stay in the streamline and the wall. This is HeLa CTCs, but if you try with NDMB 231, which are negative contrast factor, so here the PBMCs the mixture was sent in the middle. The PBMCs just follow their streamline, whereas the NDMB cells have gone to the walls. So this just shows pictorially. So the mixed population was sent in the middle, and here the PBMCs just stay near the center, and the cancer cells have migrated to the wall and get separated. But in the other case, they are all sent in the side inlets, and the PBMCs follow the streamline, and only the HeLa cells migrate to the center. So this is after receiving the outlets. You can see most of the CTCs were recovered. So you got average recovery of about 90%, and enrichment close to 50%, and similar numbers from both CTCs were obtained. So the future perspective is what is required is you need to develop a novel microfluidic platform for mechanical analysis of single cells. So single cell technology is becoming increasingly popular. We need to understand mechanical properties of single cells, and one needs to obtain quantitative insight between the cell properties and cell function. So that is one area where one can work on. And we need to develop microfluidic platform for mechanophenotyping as diagnostic and drug screening tool. Let's say you have a cell and you treat with some drug and you want to know the effect. Or you want to screen for some disease, so you can use this platform for diagnostic purpose. The challenges in translation from scientific to clinical application, because most of these experiments have been done, studies have been done using cell lines. So one is to apply these methods to real patient samples, and throughput is always a limitation. You want to screen more and higher amount of volume of sample. Also, automation in analysis is very important to be able to take it to clinical application. With that, thank you.